you got it. Okay,
Okay,
thank you.
okay, thank you.
I went somewhere and then I got it.
Yeah, it's okay. It's okay. Yeah, am I audible?
Yes, you are audible clearly. Yeah.
Okay. All right, and you can see the screen also. All right, so I think let me start from where I ended in the last class. So we essentially said that the DFT energy, which is a functional of rho density, has 5 components. One was a kinetic energy part, which I call it T of rho, and we saw that there is a problem here. Then there is an external potential. This is a one-body potential for each electron. So that is a simply integral with the V of R with the density. So these two takes care of the kinetic energy and the one electron interaction. And this is actually for molecules coming from the nuclei. So this is the interaction of the electrons with the nuclei. It's a one particle interaction because each electron with all the nuclei, but nuclei are fixed in position. So it's basically a Born-Oppenheimer approximation. So this is a Can you see the screen now?
Yes, we can see the screen.
Yeah. Okay. Thank you.
Somehow it got muted.
It got. No, I think it just lost the connection.
Shubhajit become the host.
Oh, doesn't matter. I'm a good
No,
host.
it's okay. No, he's talking of different host. Host to this Zoom event. All right. So then you have the exchange part, and we said that this exchange part is difficult because even in the Hartree-Fock, it cannot be written in terms of product of density because the two orbitals get exchanged. So it is very hard to write a local form of the exchange. And then something which is not there in the Hartree-Fock at all, and that is the Coulomb interaction. So we said that these two parts, this exchange as well as the kinetic energy, is a non-local part. Exchange because of the nature of the exchange itself, kinetic energy because it's a Laplacian operator, and the Coulomb part is of course completely parametrized. So we have 5 parts, and so this was a difficult part, and we'll come back to this today, and along with that the basis set discussion. These 2 parts are exactly explained, the external potential and the Coulomb part. And in many applications, of course, the exchange and the correlation will be put together. So most of the DFT, once I know how to take care of the kinetic energy part through the Kohn-Sham expression that we talked of, and I'm going to mention that today, all that the DFT will vary is in the exchange correlation part. So very often 2 together is just called EXC. So this is where we ended, and I will now, for today's class, I will have to start from the kinetic energy. I want to mention here that the kinetic energy part was discussed by Thomas and Fermi long back, long before the Weinberg theorem. This was actually done for the homogeneous gas, electron gas, in which the kinetic energy was written as integral rho to the power 5/3 of dq vector. If you remember our definitions on yesterday's class, this is again a local energy, local functional, because this depends, each of these evaluation depends on a particular value of rho to the power 5/3 at a particular point. However, this completely failed. So Thomas Fermi method and any correction of Thomas Fermi, in fact, people tried to correct Thomas Fermi by, in particular, Weizsäcker, that failed for atoms and molecules. So that really proved a big bottleneck for the application of DFT to atoms and molecules. Still, and even the Weinberg and Kohn theorem, although they put it in the perspective, that did not solve the problem. So till Kohn and Sham in the late 70s came up with an ingenious way of solving the problem. So Kohn-Sham, today it is known as Kohn-Sham formulation of DFT. But the essential idea was to solve the kinetic energy. So that remained the bottleneck. And after the Kohn and Sham formulation, the DFT took a huge lift. And you can see from the 80s, there are so many programs of DFT, so many applications of the DFT. I will not talk much about it, but I should also mention that the DFT derived from an excellent pedagogical formulation by Mel Levy. And those who are interested to read Levy's interpretation of the Weinberg-Kohn theorem, not just Kohn-Sham formulation. So I think Levy did a lot of work in the early part of the DFT. So let me now come to the Kohn and Sham formulation. I told you that since kinetic energy, they could not write as a functional of density directly, what Kohn and Sham did was to actually bring back the concept of the orbitals, which was not supposed to be there, in the Weinberg-Kohn theorem. Because Weinberg and Kohn theorem said that everything should be written in terms of only three-dimensional quantity. But as soon as you bring back the spin orbitals for each electron, so n of them, which means you now have variables which are for each electron one spin orbital. So even in this, just by the special orbitals, you have 3n. But if you include spin, it's even more. So this concept obviously goes away from the original idea of Weinberg and Kohn, but this was an acceptable solution because the number of orbitals that Kohn and Sham brought in are still n. Whereas in ab initio methods, anything that is better than Hartree-Fock has orbitals which are much more than n, because they involve excitation to what are called the virtual orbitals. So that number is very large. So that way, in that sense, it is still a simplification, and it actually simplifies as much as Hartree-Fock. So Kohn-Sham formulation is not as simple as what Weinberg and Kohn originally envisaged, but it is still much simpler than the ab initio methods. So that's the whole idea. It is almost as simple as the Hartree-Fock. But certainly original formulation, as if you remember, was supposed to be much simpler because the entire energy was supposed to be only written in terms of three-dimensional quantity, whereas in Hartree-Fock, you still have n spin orbitals. Each of them is a one electron function. So you have a lot more variables. And of course, when you go beyond Hartree-Fock, like perturbation theory or CI or coupled cluster, you have too many variables. So this became a kind of a compromise. So Kohn-Sham kinetic energy kind of became a compromise to doing the DFT. So without going into too much details, what Kohn and Sham did was to, as I said, was to bring back the spin orbitals. So for example, if for an n electron, Kohn-Sham assumed that each electron occupies a spin orbital. This is exactly what the Hartree-Fock assumes, and this is what exactly the chemists want, that an electron in a spin orbital. However, remember the electrons are indistinguishable. So which electron is in which spin orbital, you cannot tell. But if there are two electrons, there are two spin orbitals, that is all that matters. So let me call those, those spin orbitals as chi1, chi2, chi3 to chi-n. Now, remember, each of them is an orbital. So spin orbital. So orbital has 3 dimensions and a dimension of spin. So I am bringing in 4 dimensions for each of them. So if you add up, this is a 4n dimension problem. So as you can see, the problem is no longer as simple as DFT originally assumed, but it is almost as simple as the Hartree-Fock. The Hartree-Fock exactly has the same problem, that each electron occupies a spin orbital. So it became as complicated or as simple as the Hartree-Fock, but certainly, again, I'm repeating, not as simple as the original formulation of DFT. So assuming that now each electron is in one spin orbital, one can even think of a fictitious wave function, which is just like a Hartree-Fock wave function, where a determinant is there, anti-symmetrized product is there of electrons in n spin orbitals. So that is essentially the idea that the Kohn and Sham proposed. Although the wave function does not come in the picture, as you will see, it is more in the mold of just the spin orbitals. What is important is the association of these spin orbitals with the density. So that is a very important part. Now note that each of the spin orbitals, let's say chi-I, has a part which is space part, phi I, and a spin part which is either alpha of omega or beta of omega. So omega is the spin coordinate, and here you have a space coordinate, which I can phi of r vector, which is 3-dimensional. So that's how the 4-dimension is coming. So what this can be written as, the density can be written as in the following manner, that you sum over all the spin orbitals, which is basically chi-I r omega, sum over all of them, square or modular square if it is a complex function, because you remember the bond interpretation, the probability density is psi star psi. So it is actually chi star chi, which is nothing but mod chi square. So yeah, I should say mod chi square, okay? R omega, and then you integrate over all the spin. That means spin is being summed up. This is a formal way of writing the density. Let me write it again. And this is sum over all the spin orbitals. This is a mathematical way of writing the density. The density is, again, let me write it, sum over I equal to 1 to n, integral chi-I star, and the density has 4 dimensions, r omega, chi-I r omega, that can be written as mod chi-I square, and then you integrate over the spin. So once you integrate over the spin, you get a 3-dimensional quantity. This turns out to be what we did in the very first class, if you remember, in the Hartree-Fock. Like, for example, we discussed the problem of helium, where there are 2 electrons. So essentially 2 orbitals are there. One is a chi-1, which is 1s times alpha. Another is a chi-2, which is 1s times beta. Again, it's very simple. Very early in the quantum chemistry, we teach this. So you have a 1s orbital with the 2 spins, alpha and beta. If you do this integration, it means your density for this will then become mod 1s orbital, just the orbital, square times 2. This 2 is coming because of this integration. So you do integration is nothing but sum. So you sum over the alpha spin, sum over the beta spin. So you get 2 mod 1s square. I also gave an example of, let's say, lithium atom, 1s and 2s with alpha spin. And here the density would be 2 times mod 1s r square plus 2s mod r square, because there is only one electron in 2s. So I multiply by only one. So basically, you take the orbital square, you take only the orbital square, the special orbital square, and simply multiply with the number of times the orbital is occupied. Each orbital is occupied. That takes care of integration over the spin, because the spin alpha and beta are really orthonormal function. So when I integrate between alpha star alpha or beta star beta, is just one. So basically, it is just taking care of the occupation. So simple way to think of this, and this will give you an example how to calculate the spin from the spin orbitals. The spin orbitals are here, chi s alpha, 1s alpha, 1s beta, here 1s alpha, 1s beta, 2s alpha. So I'm summing 3 times, 2 plus 1. So the density can be obtained very easily from such a 1 electron spin orbitals, as I wrote here. So what Kohnenstamm said, that although I have just the spin orbitals, these spin orbitals will immediately give me density. So I can join the Kohnenstamm, I can join the DFT by saying that I know at least the density. That still doesn't solve the problem. I have to now write down what is the kinetic energy. So the kinetic energy was written by using the fact that now I have n spin orbitals. It's very easy to write this kinetic energy. Assume that I have a wave function. So assume that I have a wave function which is a determinant, just like in the case of Hartree-Fock, containing n spin orbitals. And then what will be the kinetic energy operator? A kinetic energy value. Note that the kinetic energy operator is minus half Laplacian. So if you take all these spin orbitals, chi1 to chi-n, then your total kinetic energy will become sum over each of these spin orbitals, and then calculate for each orbital the matrix element of the Laplacian, 1 electron Laplacian, with respect to the each operator. So this is a second derivative operator. It's a non-local operator, but you can calculate the integral. This is done routinely in all ab initio methods, and this is called a 1 electron integral. It's very simple. Sum for all the n spin orbitals. So that becomes your total kinetic energy of the n electrons. So your total kinetic energy for the n electrons is a sum of kinetic energy average for each spin orbital. Because of course, if I do for each spin orbital, that is sufficient, because I know that each electron has 1 spin orbital. So basically, if I sum over, I'm summing over the individual kinetic energy of the electron. So it is very simple. So if I have a system like helium, then I have 2 electrons in 1s alpha, one of them in 1s beta. I find out what is the kinetic energy for 1s, what is the kinetic energy of the 1s with beta. Of course, they will be identical for alpha and beta. So you just sum them up. So that is exactly what is done. So what is the kinetic energy? Do this integral. This integral evaluation is fairly simple. Okay, these are mathematics, but these are fairly simple. This is a second derivative operator, which can be written as sum of the second derivatives in Cartesian. In spherical polar coordinate, it is somewhat more complicated. And you have an orbitals which are in spherical polar coordinate r theta phi. You can do the integration and do the summation. So we will not worry how to do it, because these are mathematics, but these mathematics are easy to do. And this is what is done in Hartree-Fock routinely in ab initio methods. So in exactly taking the Q, you can calculate the kinetic energy. Now this is a very elegant formalism, because it goes away from the original concept of DFT. by bringing in n spin orbitals. Further, these n spin orbital, just like in Hartree-Fock, they can be assumed to be orthonormal. Orthonormality essentially means that if you take two different spin orbitals and integrate among them, it is zero, which means the spin orbitals do not overlap, two different spin orbitals. If you take the same spin orbital, it is normalized to unity, 1. So that is the meaning of the orthonormal. So you have n spin orbitals which are orthonormal, and then, as I told you, rho of r, which is nothing but sum over these n spin orbitals and integral mod psi squared integral d omega. Please remember, sometimes I wrote chi I star chi I, sometimes I'm writing mod chi I square. They are identical. So this is nothing but mod chi I square. Okay, this. So it's identical. So if I do this, since chi i's are orthonormal, is sum over all n, it is very easy to show that the integral rho of r d cube of r equal to n. So remember our condition. Whatever we do, you must have this condition, and that will be required for the Weinberg-Kohn theorem too. That condition is automatically satisfied if you assume that the n spin orbitals are orthonormal. So that's a very important assumption, and that will ensure that the density, if you sum over the entire electron density, it should give you total number of electrons. And that is the whole idea. The density, if you count the density over the entire space, what it should be always the total number of electrons. It can't be more than the total number of electrons or even less. If it is less, that means you're missing some electrons. So it should be exactly the total number of electrons. And that is assumed, that is automatically satisfied because rho of r can be written as sum of the spin orbital densities. And since the spin orbitals are orthonormal, it can be automatically shown that this normalizes to n. With this, and the fact that the kinetic energy can be written in this manner, now we come back to the business. However, we already know that the fact that the kinetic energy is a sum of just average kinetic energy for each spin orbital is an expression that was there in the Hartree-Fock, right? In the ab initio method, but the Hartree-Fock itself is not exact. So obviously, this formulation of K's formulation of kinetic energy is also not exact. But you can make it quite close to the exact, just like the Hartree-Fock. Hartree-Fock is not bad, it is exact, not exact, but it is close to the exact. So this K's formulation of kinetic energy is not exact, but much better than the Thomas Fermi. The Thomas Fermi kinetic energy. The rho to the power 5/3 that I talked of for the homogeneous electron gas. So there is still a residue error. So there is a residue error of the kinetic energy that will eventually padded up in the EXC. Remember, in the EXC, I still don't know how to do it. I have to come back to the exchange and the correlation. But the point is that whatever is the residue error, I am going to do some kind of parametrization here. Automatically, the residue error will be padded up here. Because when I'm going to parametrize, I'm going to parametrize this with respect to the total energy. So whatever is missing will now come here. So that is something that I want to make as a comment, that this is not an exact kinetic energy. So whatever Thomas Fermi wrote, it's an approximate kinetic energy. Many people call it Thomas Fermi kinetic energy. It's just a Thomas Fermi kinetic energy, but it is pretty good, and the residue will all be taken care in the exchange correlation function. So if you look at the 5 parts, I had the exchange and the correlation. So here I'm going to take care of the residue error. Okay, so that is something that I will come back. We'll come back when I discuss the exchange correlation. But as of now, it's a comment that the kinetic energy can be, once you have n spin orbitals, you can write down the kinetic energy. Of course, the question that you will ask me, how do I get the n spin orbitals, right? So he brought back the n spin orbitals, and that obviously will come when I calculate the density, and that will be the content of the now second Weinberg-Kohn theorem. Remember, your second Weinberg-Kohn theorem would calculate the density. So very similarly, your second Weinberg-Kohn theorem will now calculate these chi's, chi1, chi2 to chi n. So we will have to define these Weinberg-Kohn theorems, second Weinberg-Kohn theorem, somewhat different. We will see how to define it. Once we can write the kinetic energy part as sum of the orbital kinetic energy, individual orbital kinetic energy. So here, of course, the density will not feature explicitly. It now features the n spin orbitals. Then the problem now will be when I do the Weinberg-Kohn theorem, one term has spin orbitals, other terms have density. At least these two terms, and these two terms still we do not know. But let's assume that I have an approximate form of exchange in the correlation. The LDA that I talked of was a form. You can go beyond LDA, and we will also discuss some forms of the correlation. But let's assume that they are there. But even then, the problem is that this has orbitals, this has density directly. So how do I grapple this problem? Because in Weinberg-Kohn theorem, second, if you remember, we were supposed to make these stationary with respect to the density. So densities are here in all the terms, but not here. They have the n spin orbitals. But I know how density can be related to the n spin orbitals. But I still cannot write these, although I know that, that the kinetic energy is a sum, let me see, kinetic energy is sum of the individual orbital density, and density is a sum of the orbitals square integrated over spin. I cannot write this expression in terms of the density because there is a Laplacian here. This is a little bit of mathematics, and that is why I said it's a non-local operator. I cannot get in form of density. If I could get, then of course I told you that's a problem which is a very, very big problem to solve. I can write kinetic energy in terms of density. So many people have tried to do that, write chi star, chi as density, sum, but because of this operator in the middle, you cannot write it as a functional of density. So this is a very fundamental problem of the kinetic energy. I talked about it in the last class, and I'm repeating. So what I have to do is that this term, the kinetic energy term, I cannot write in terms of density. So what do I now do? I go back and change my strategy. All the terms which is density, I will write in terms of spin orbitals. So this term, this term, these terms, and these terms. I'm going to rewrite these terms by density because now I know how to write density in terms of orbitals. That is easy. So basically the strategy before I do Weinberg-Kohn theorem, that all energy terms which are in terms of density or rho of r will now be written as the spin orbitals. Through this expression, that rho of r equal to sum over chi I square integral d omega. This is easy. In kinetic energy, I had to do the reverse. I had expression in terms of kinetic energy, spin orbitals, I had to go and write in terms of density. That was very difficult. But here I have expressions in terms of density, I have to simply expand the density in terms of spin orbitals, and I will automatically get. So the reverse process of transferring the density to spin orbitals is very easy. So all these terms, these terms can be written easily in terms of spin orbitals by expanding. Again, I will not do the mathematics, but I'm just telling you the strategy. Here, I had written down already in terms of spin orbitals. I could not write in this form. So this could not be transformed to the density, but this can be transformed in terms of spin orbitals. So what is finally done is that all terms, all the energy expressions, all terms are now expanded in terms of spin orbitals only. So it basically became like a Hartree-Fock. In Hartree-Fock, everything is written in terms of spin orbital, except that the Hartree-Fock did not have anything which is correlation, because Hartree-Fock was exactly missing correlation. So did not have any term which is EC of rho. And Hartree-Fock exchange could not be written in terms of density at all. So any EX that I'm going to write here is going to be an approximation that I already told you, but that I will not worry right now. But whatever is I write, it is possible to write this in terms of density and eventually in terms of the spin orbitals. So all expressions of energy are now in terms of spin orbitals. So how does the Wenbach-Kohn theorem, second Wenbach-Kohn theorem change now? You remember the second Wenbach-Kohn theorem? We said it is del E del rho equal to 0, subject to the condition that the integral rho of R integrated over the entire space is equal to the number of electrons. Now that everything is in terms of spin orbitals, I have to redefine this variation. So now the rho is does not there. What is there in terms of spin orbitals? So what this second Wenbach-Kohn theorem would now do is to write the energy expression, first derivative, in terms of the spin orbital. So let's say a specific spin orbital chi I, star of that. Remember the spin orbitals have, R and omega. Spin orbitals are there is with a conjugate because each row has chi I star, chi I. So I can take any one of them. So let's say chi I star equal to 0. So they become my basic variable. So instead of density, spin orbitals become my basic variables, and I make this equal to 0. And how do I make this condition? I make this condition by saying that these spin orbitals are orthonormal. I already talked with you that the spin orbitals are orthonormal, which means if I integrate completely two different spin orbitals, it is 0. The same spin orbital, it is 1. I hope those who are not aware of this function, this is called the Kronecker delta in mathematics. This is 0 if I is not equal to j, and this is 1 if I equal to j. So if I is equal to j, the integral is 1. If I is not equal to j, the integral is 0. So that means that different orbitals do not overlap. Same orbital, the integral is 1. And I told you, if this condition is fulfilled, then the density integrates to n. I think I had already told you. I just want to repeat that part. Somewhere I talked about it. Yeah, so I said I had talked about it, that if n spin orbitals are orthonormal and I define density in this manner in terms of the spin orbitals, then the density integrates to n. So these are the three equations. I'm using this equation to simplify energy in terms of spin orbitals. I have to subject the Weinberg cone to this condition, which means I will subject them to n spin orbitals being orthonormal because this is identical. So I have a little modification of the second Weinberg cone theorem, that instead of writing this as my condition, I now say that this energy expression with respect to each spin orbital variation is 0. So this is the first derivative, which is 0, subject to the condition that the spin orbitals are orthonormal. So they are the Kronecker delta. So this becomes a little variation of the Weinberg cone theorem in the Kohn-Sham formulation. Please let me know before I proceed if there is any question. If there are none, I will proceed. Okay. Hello, am I audible?
Yeah, I think it's quite clear. Thank you.
Okay, fine.
Yeah,
Okay.
yeah.
So I will now proceed. Because of the fact that I'm writing everything in terms of spin orbitals, it actually becomes like Hartree-Fock. Now there is no difference from the Hartree-Fock, except that I have a correlation part, which is different from Hartree-Fock. I don't know how to write it, but formally I have. I have also exchange part. We'll see how to write it. But Hartree-Fock knows how to write exchange exactly. We can replace that, and we will see that people will try to do that. That why don't you take the Hartree-Fock exchange? Because anyway, you are taking Hartree-Fock spin orbitals. So this will become like a Hartree-Fock theory. And if you remember the Hartree-Fock theory, we get the spin orbitals in Hartree-Fock by solving, I will not write details of the mathematics, by solving a one particle equation, like a eigenvalue equation, which is like a Schrodinger equation, one particle eigenvalue equation. So you get now the spin orbital exactly like this. So let me call that, I'm just writing the one particle equation, and that has an operator, which is one particle operator, f of r comma omega, then chi of r comma omega equal to an energy multiplied by r comma omega. So this is an operator, one electron operator. It acts on a spin orbital to give you a number times the spin orbital. These kind of equations, again, for those who are not aware, are called the eigenvalue equation in mathematics. Hartree-Fock uses that all the time. So those who know Hartree-Fock will understand DFT. It's very similar. Now, this is called an eigenfunction. This is called an eigenvalue. So all we need to do is to solve a one particle equation where this will be defined. The problem will be in this definition of the Fock operator, because of the Coulomb exchange and the correlation part, this will itself depend on these spin orbitals chi-i's. So you don't have an a priori form of the Fock operator unless I know this. Unless I know this chi-i's. So this equation, the eigenvalue equation that I wrote, is solved in an iterative manner. Once again, those who are aware of a little bit of mathematics, in mathematics, this is a very common procedure, which is called iterative procedure. Since I don't know the Fock operator, unless I know this, I have an approximation of Fock operator, solve this, get an approximate chi-i, then recompute this Fock operator now with all the terms, again solve the eigenvalue equation, again recompute, you keep doing till the input and the output spin orbitals match. This procedure is very often called the SCF procedure, self-consistent field. Those who are again aware in the Hartree-Fock, you know that the Hartree-Fock is very often called the self-consistent field procedure. And this is exactly the same in DFT, except that now it is within the DFT. So very often it is called KS-SCF procedure, Kohn-Sham self-consistent field procedure. There's a difference from the Hartree-Fock in the treatment of exchange and the fact that I have been repeating the Hartree-Fock does not have correlation. So it's a completely different. So it's a very, very different. So the procedure otherwise is very same, or I should say similar as Hartree-Fock, except the form of the exchange is different. And of course, the EC of rho is completely absent in Hartree-Fock and is present in DFT. So that's a very, very important, that is a very important part. And here I must pause to tell you what I have been saying before, that although the DFT is very similar to Hartree-Fock, remember I have been saying computational cost is similar, but DFT is better than Hartree-Fock in accuracy. And now you will appreciate why. First is that the exchange term is a bit different, but most importantly, the correlation part was completely absent in Hartree-Fock, but now it is present in DFT. Although there will be a one particle form, and that's the beauty about the DFT. It is present in DFT, but absent in Hartree-Fock. So hence, although the computational cost is similar, but DFT is more reliable. Than Hartree-Fock. The problem with DFT is still that when I'm taking this different exchange and I'm including correlation, it is not done from a first principle. So it's not still systematically improvable. But because at least there is a semblance of EC, which is completely absent, this is completely absent in Hartree-Fock, the results are usually better than the Hartree-Fock because some amount of correlation comes in, but Hartree-Fock does not have any electron correlation. And this is the reason the statement that I have been making that DFT is a very good compromise comes mainly because of this part, that at the end DFT becomes like a Hartree-Fock equation, eigenvalue equation, solved in the same manner, self-consistent field, but it is different that the correlation part is absent in Hartree-Fock, present in DFT. Hence, although the cost is similar, DFT is more reliable. And that's a very, very, very important statement between DFT and Hartree-Fock. Is this part clear? So I'm just trying to do as much qualitatively as possible without going into these statements. So some of the statements often lack a little bit of a rigor, but I think it's generally true as a general reason why DFT is a compromise method. Okay. So now that we understand, our equation becomes a Hartree-Fock equation, like equation. Many people would like to include Kohn-Sham here, just to indicate that this is a Kohn-Sham Hartree-Fock equation. Very similar. This is the same equation that I wrote here. I wrote all the variables R, omega, etc. I had stripped them off, made it look much simpler as an eigenvalue equation. This is in terms of spin orbitals. I think there is a little thing to do, that the same equation can be written in terms of space orbitals only. So three-dimensional orbitals, phi I R. So the Hartree-Fock equation will become F Kohn-Sham. There's a slight difference in the operator, but don't worry about it. Phi I F R equal to epsilon I phi I F R. Exactly the same. So you get what are called the Hartree-Fock space orbitals, like 1s, 2s, etc. And in this case, it will become Kohn-Sham, because I have a Kohn-Sham operator, DFT orbital. And these eigenvalues are what are called orbital energies. So all of you have heard this term orbital energies. And if you have highest occupied orbital, this energy will correspond to the HOMO. The lowest unoccupied orbital will be called the LUMO, and so on. Although you don't need more than n spin orbitals, from this equation, you can get more than n spin orbitals. So this equation will give you more than n spin orbitals. That's in the nature of the mathematics. But we don't need more than n spin orbitals. So the rest of the spin orbitals are what are called the virtual or unoccupied orbitals. And the lowest of them is very important. It is called the LUMO. The highest of the n spin orbital is called HOMO. The lowest of the unoccupied orbitals is called LUMO. And they have a very important theorem that if I take the negative of the highest occupied orbital, which is called the HOMO, this is called the lowest ionization potential. So if I want to ionize an electron easily, it will ionize from the HOMO highest occupied orbital, and the negative of that orbital energy is going to be the IP, or ionization potential. Very often it is called the vertical ionization potential, because we are doing everything under Born-Oppenheimer approximation. So it's like the nuclei remain in position. And similarly, if you want to add an electron to the system, if you add it to the LUMO, this will be called vertical electron affinity. So many of you know the IP and the EA. They have a very simple interpretation once I get the orbital energies. So the orbital energies have a physical significance in terms of the ionization potential and excitation and electron affinity, which is basically adding an electron or taking out an electron. So if you want to know how much energy is required to ionize an electron, the result will be minus of epsilon HOMO. Remember, epsilon HOMO, which is the orbital energies, are always negative if it is a bound state. So the negative of that negative is always positive. So that's why we say we require energy to ionize. But the LUMO can be positive or negative. Depending on that, electron affinity can be positive or negative. So if this is positive, then it is very difficult to attach an electron. If this is negative, then the electron affinity becomes positive, so you can easily attach an electron. So the anion state will also become stable. So positive electron affinity indicates that the anion is stable. You always require energy to ionize an electron, but if you put an additional electron, you may gain some energy if the electron affinity of the system is positive, and that will be determined by the negative of LUMO. These methods are actually there as a Koopman's approximation in the Hartree-Fock, and you have a very similar Koopman's in the case of the DFT, which are often called extended Koopman's theorem, or there are people who call Yanak's theorem. Again, I will not go into the details, but I just wanted to mention that many of the experimentalists, after they do the calculation, they require these quantities. Many times you actually like to write down the excitation energy. And it is very, I should say, tempting to write the excitation energy between the difference of LUMO and HOMO. But that is very dangerous. So for example, if I have a HOMO energy here and the rest of the energies are low, and then you have a LUMO here and the rest of the energies are up, this is the energy going up. So very often you tend to associate these as the excitation energy. Energy required to ionize an electron from HOMO to LUMO, right? I mean, that's a normal tendency. But the difference of LUMO and HOMO as excitation energy is not at all accurate, even in the context of DFT. So it is much more accurate to say that the negative of the HOMO is IP, negative of the LUMO is electron affinity. But this still gives you a gross idea of how much energy it is required to excite an electron from a highest occupied orbital to the lowest unoccupied orbital. All right, I should now mention at this stage that once I have come to this equation to get the molecular orbitals, which are spatial orbitals, the very interesting thing starts to happen. This equation, unfortunately, even though looks very elegant, is very hard to solve for molecules. So either the Hartree-Fock, and this is now same for Hartree-Fock, or the Kohn-Sham one particle equation is very hard to solve analytically. For atomic systems, only for atoms, solutions, again, mathematical solutions by numerical methods, numerical solutions are possible or exist. But for molecules, even the numerical solutions are very difficult, or they will have a lot of error. So people, I can't do analytically, I can't do numerically. So for molecules, the issue then turns out to be, how do I solve this equation? So it's very nice that I have got a very elegant eigenvalue equation, but I just wanted to mention that this is true even for Hartree-Fock. So now whatever I will do, I do for Hartree-Fock also, because the equation is exactly like Hartree-Fock, except that this operator is different. I repeat again, this is different because of the fact that I have this E correlation of rho in the DFT. But the rest of the procedure for solving for molecules is quite complicated unless you adopt a procedure. This procedure was originally what I'm now going to write. That procedure is called introduction of bases. And now you see, I'm coming to the basis set. It is called the introduction of bases and was first formulated by Clemens C.J. Ruthan in a very seminal paper in the early 1960s. And this is called the Hartree-Fock-Ruthan equation. The very same idea will be done here because there is nothing different now from the Hartree-Fock. So what will be done is to introduce the bases, and I suffice to say that instead of an operator eigenvalue equation, you will get a matrix equation, almost near eigenvalue. They call it pseudo eigenvalue equation. I will not actually try to expand that plan, but it's a matrix equation. By introducing bases, and that basis will now be the basis of molecular orbitals. So what are the bases? Sorry, the basis of atomic orbitals. So I expand molecular orbitals in terms of the atomic orbitals. And this is a very common procedure, what is called the LCAO-MO procedure. Many of you have already heard the linear combination of atomic orbitals to molecular orbitals. That is a procedure that is solved. So let me write down how exactly it is done. The phi that I have quoted in this equations are my molecular orbitals, phi I. These phi i's will now be written in terms of a linear combination of a basis, and that basis I'm writing the Greek symbol mu should be as large as possible because it's an expansion of one electron function in terms of another set of one electron function or basis. So mathematically, this should be as large as possible. So I call it some k, which is very large. It has nothing to do with number of electrons. K should be much larger. And I call this C mu I. These are the coefficients of A mu. These are my atomic orbitals. So the idea of doing a DFT or a Hartree-Fock is that the atomic orbitals should already be known. So these are known atomic orbitals. And then the DFT equation, when I write the matrix equation, DFT equation will then provide me these coefficients. So please note the change of the problem. My problem was that this was the unknown. My orbitals are unknown, remember. And because from the orbitals, I would have got the density. Now I'm saying these orbitals are expanded in terms of the known atomic orbitals. So what is my unknown? These are known. My unknown here are the coefficients of combinations. And that will now be solved by this matrix equation. These are numbers. I will not write the matrix equation. This is exactly what Ruth Hahn did. Matrix equation will solve the coefficients. So that I can get the coefficient. Once I get the coefficients, I can now get the molecular orbitals, phi I, or the spin orbitals, chi i's, whatever. That you just attach alpha and beta. And from there, I can get the density. I told you, I know how to relate density to spin orbitals. I forgot the density picture. I wrote everything in terms of n spin orbitals, but I can go back to the density. I can go back to the energy, ground state energy. So that will be my procedure. And in this process, you will also get these LCAO, MO coefficients. And these are very important for chemistry because for each molecular orbital, let's say HOMO, I know if this coefficient is large for a particular mu, then I know that particular atomic orbital contributes. So many times chemists say that the HOMO is controlled by the d orbital. HOMO is controlled by the p orbital. Those are the atomic orbital, d, p, etc. I can find out from these coefficients. So the analysis of these coefficients is a very important part of the output. These coefficients will be obtained by the Ruth Hahn equation. I'm repeating. So the Ruth Hahn equation is very, very important. After the introduction, it's a matrix equation. I will get these numbers and I can reinterpret the numbers. Please tell me if there is any problem with the procedure before I come to the actual definition of the A mu. And that is where the basis set will lie now.
Procedure is great. The only thing that I didn't get is why do you need a large K or scalar?
Because mathematically what I'm doing, I'm expanding a one particle function in terms of another one particle function. So in mathematics, they say that if I have a f of x, I want to expand in terms of another basis of gi of x, this must be complete. So it should be a complete basis. So one function can be expanded in terms of a complete set of known functions. So I will give you an example. E to the power x. How do I write? X to the power 0, that's 1, plus x to the power 1, plus x squared by 2 factorial, plus x cubed by 3 factorial, and so on. If you notice, each of these terms, x to the power n, 0, x to the power 1, etc., forms a basis. And these are my coefficients, 1 by 2 factorial, 1 by... But I cannot simply stop with 2 terms. It's a complete set of terms. Similarly, if I expand sin x, cos x, anything that you expand, you can expand in terms of complete set of functions. So this set of known functions, I don't know this function. I'm writing this in terms of a known functions. Mathematically, this is exact only when this known set of function is complete. What is complete? It's usually an infinite number. Like here, what is complete? Up to x to the power infinity. So if you look at exponential x, it has infinity terms. So of course, I'm not suggesting that the k has to be infinity, but k has to be large. And hence the question is, larger the basis set. And now you will understand why we always say this. Larger the basis, the better it is. That means you are doing a better calculation. Sometimes it is right, more the merrier. I hope you understand the English. Merry means you are happy, right? Merrier. More the merrier, or larger the basis, the better. Larger the better. So you have to keep on adding basis function, and there is no end to it. Yet, we have to make sure that the k is reasonable. So in the choice of basis set, very often we will be dictated by intuition. Intuition plays a very important role. How quickly I can go towards completion, what kind of basis sets I should use? Because there are so many sets. Just like I said here, gi of x. This gi of x is not just one set, that could be hi of x. It could be another basis set. There are so many complete functions, complete set of functions. There are so many one electron functions. Which one should I take? Remember, I have decided to take atomic orbitals. And I think the chemist has already come into play. Why did I decide to take atomic orbitals? Already have a question. I could have expanded in terms of another three-dimensional set of functions. A physicist will say, why are you bothered about atomic orbitals? Precisely for the reason that I mentioned. If you take any basis function, this k may have to be 10,000, 100,000 to get a reasonable result. But when you use atomic orbitals, I can get the same result with a much less number of k. Because chemist knows that the molecule is only composed of atoms. So this is where the intuition has already begun to play. So if I do, let's say methane, I want to expand the molecular orbitals of methane. I have many choices. I can expand even in atomic orbital. I can expand each molecular orbital in terms of only hydrogenic orbitals. Right? Hydrogen atom orbitals. That's also a complete set. If I take all hydrogen atom orbitals, a complete set, I can use methane molecular orbital as a linear combination of only hydrogen atom orbitals without involving carbon. And then even within the hydrogen atom, there are 4 hydrogen atoms. They are in different position. So hydrogen atom, at which position I will take, that is also important. But the chemist knows this is bad because methane has carbon and 4 hydrogen. So what does the chemist will say? Take carbon plus 4 hydrogen. All the basis sets as much. And then you can get a very good result with less number of basis functions. And I'm going to come to that now. This question actually prompts me to the discussion of the basis function. I will not take only from one atom. I am going to take basis functions from each atom. But the mathematics does not tell that I have to do that. Mathematics only said, expand this in terms of a complete basis. But the fact that I'm taking this basis function as atomic orbitals is already a recognition that the molecules are formed of atoms. That's the first. Then the second is I spread over all atomic orbitals because I also know it is foolish to discuss methane in terms of only one hydrogen atomic orbitals. If you take carbon, so this entire LCAO-MO, picture, I would say, is the intuition. This particular, not the introduction of basis. Introduction of basis is physics. LCAO-MO is a specific basis, that is chemistry. So when I looked at this summation, that is just physics. Any basis, complete set. That's a physics, no problem. It can be any basis. So that is a phase physics. As soon as I say that these are atomic orbitals, this is where chemistry comes in. Chemistry will further tell you that if you have a polyatomic molecule or a diatomic molecule, do not take only one atom. Take all the atoms. So the entire concept of LCAO-MO is driven by chemistry, and chemist tries to interpret. Because now, if they are atomic orbitals, these coefficients have a meaning. I can say which molecular orbital is driven by which atomic orbitals. So chemistry will come into play. So when you do DFT or Hartree-Fock, chemistry is very important at the end. So far, we have tended to do physics. Whether Hartree-Fock, DFT, that's a physics anyway. But at this point, we are beginning to get into the chemistry. So the basis set is a very typical chemist jargon. If you go to physicists, they wouldn't bother. The particular basis sets that we use, like 631G, whatever, I'll come to that a little bit later. So the point that Subhajit mentioned is very important, that we do not want to use infinite basis. We want K to be large, but not very large. So again, there is a compromise. So compromise value of K should be large enough. So when I use atomic orbitals, that compromise can be reached. Is that okay?
Yes.
Yeah, okay. So let me now describe how do you do the atomic orbitals. What kind of atomic orbitals? So the fact that I was in methane, I can take an example of methane and continue to do that. If you want, I can take a simple example first, maybe a diatomic molecule. And let me say I take a lithium hydride, a very simple diatomic molecule. So what does the basis set now look like? It must have atomic orbitals of lithium. It must also have atomic orbitals of hydrogen. The orbital function, and that's a function I will mention, not only is just a function of r theta phi, as all of you know, 1s orbital is r theta phi, function of r theta phi, but it also depends on where the atom is positioned. If you are talking of a single atom, this position does not matter, because you can always assume that that's the origin. But when you have a molecule, there is a relative position. If this is the origin, this cannot be the origin. They are in different points. So when you define the atomic orbitals, we have to remember the position of the lithium atom and the hydrogen atom. So even if you have a hydrogen and hydrogen, dihydrogen molecule, I take atomic orbitals of hydrogen, but I have to take atomic orbitals of both hydrogen, hydrogen 1, hydrogen 2, because they are not in the same position. If you remember hydrogen atom, I will just go back to very, very basic quantum mechanics. You have an orbital, which is called the 1s r theta phi. if you again remember that this function does not depend on theta and phi. So the theta phi is basically a constant. It has only a normalization constant. And then only an r part, which is just exponential minus r. There is no theta phi part. Sorry, this is r theta phi. This is not a vector. I'm sorry. Because the vector has been expanded into a r theta phi, spherical polar coordinate. So r divided by a naught. A naught is a Bohr unit of length. So r by a naught becomes a dimensionless quantity, and that is very important. So an orbital like 1s orbital simply becomes a number at different r. So I can get a 1s, and then the density is nothing but 1s mod 1s squared. So I have the density of the hydrogen atom at different r. So I think people should know the hydrogen atom very well. So, but here I don't have a position of the hydrogen atom, because this hydrogen atom I can assume at the origin. But when I go to the hydrogen and the hydrogen, if I'm taking 1s orbital only, I still have to define a position. So let's assume that the origin is the 0 point, and I have a distance which is in z direction or whatever. This is a z direction. It has an r, which is, let's say, minus 1, 0, minus 0, 0, minus 1, and 0, 0, 1. So I'm just defining in some atomic unit, let's say 2 atomic unit in z direction. Then what is going to happen here, that I have to define in r theta phi, or at least in the r coordinate, their distances. So I should transform this into r theta phi, and I will call this r1, this is r2, and it has, let's say, r1 theta 1 phi 1, it has r2 theta 2 phi 2. So I'm just going over to the spherical polar coordinate, and then this hydrogen atom 1s orbital will be now exponential minus r minus r1, sorry, r minus r1 divided by n. And this will become exponential r minus r2 divided by n. Because
Hello.
Yeah, we cannot hear Professor Paul.
Yeah, so I think it's disconnect. He
I
disconnected.
lost it again. I lost it again. Yeah.
Yeah, Ken has some problem today. Okay, so maybe now he's back.
Now we are.
Yeah, that's okay. Yeah. So for the hydrogen atom, we don't write, because the origin is at 0, 0, 0. So I don't have to write this. But for a molecule, the two hydrogen atoms are different position. So I have to subtract the R1 and R2 from here. Okay. So the coordinate of the atoms have to be subtracted from the R values. So when I say atomic orbitals, this is the form of a 1s atomic orbital. And of course, other orbitals, 2p, p orbitals, etc., are more complicated, but they have a form which is very similar to this. What is important in this form is this exponential minus r, minus some r alpha, the coordinate here, okay, in some sense. So this is very, very important, coordinate of the at the nucleus, whatever is, let's say, the alpha nucleus. So this is a very important part in all these atomic orbitals, and these are usually called the Slater atomic orbital. Okay, I can write this in the vector term just like this, but actually what happens is that for a 1s orbital, only the distance will come, but for p orbitals, etc., it will r theta phi. So I can generally write like this. the coordinate of the atom has to be subtracted. And of course, there are other terms. It is proportional to them. But this is a very, very seminal term. And then there are theta phi terms for p, d, etc. For s orbital, there is no theta phi. I don't want to go into the details of the atomic orbital, but these orbitals are called the Slater atomic orbital. Okay? And this essentially means that if I have a dihydrogen molecule, I have to take hydrogen atoms from this and this as well, because they are different. Because now I'm subtracting this R alpha. They're different. If I do methane, I have to take all the 5 atoms. If I do lithium hydride, I have to take from lithium and hydrogen. And then form my entire basis set. So that's the idea of the basis set. The question is, I come back to now methane and say how many I have to take, because you see, I talked about K, capital K, and I told you as large as possible. But what is the minimum that you should take? So if I'm doing the carbon, the minimum that I should take, the chemistry again dictates me, is 1s, 2s, 2p. I think all of you will agree. Because carbon atom has 6 electrons, and the atomic structure is 1s squared, 2s squared, 2p squared. So at least this much I have to take. For hydrogen, each of the hydrogen, 4 hydrogen, I have to take at least 1s. Each of them 1s. Nothing less than this is acceptable. I hope all of you realized. This basis is called minimal basis. I hope you immediately understand why I'm calling minimal, because this is the minimum that you can take. You can now calculate the number. What is the capital K that you are generating? For carbon, 1s function, 2s function, and whenever I write 2p, it means it is 3 functions, px, py, pz, don't forget. So 5 here, 1 here, 1 here, 1 here, 1 here. That's 9. So if you are doing a methane calculation in a minimal basis, your K is 9. I hope it's clear. If your K is 9, remember my expansion. Sum over mu equal to 1 to K, C mu I, A mu. So you have a 9 number of atomic orbitals. How many molecular orbitals will generate? 9, right? You know a very simple philosophy. If you linearly combine 2 atomic orbitals, you should get 2 molecular orbitals. 9 will give you 9. How many I require for Kohn-Sham DFT? Remember, these are special orbitals. So 9 means 18 spin orbitals. I require only 10 of them because methane has 10 electrons. So n spin orbitals, you remember? So I require only 5 of them, doubly occupied. Those are my occupied molecular orbitals. And how many unoccupied MOs I have got? 4. So it's very simple. These are totally unoccupied right now. Or 8 spin orbitals, 10 occupied spin orbitals. So in terms of spin orbital, you double this, 10 and 8. Because this is a closed shell system. All are doubly occupied. So you generate occupied as well as unoccupied orbitals to do whatever chemistry you want to do. So this K is called the minimal basis. Is it clear? Of course, these 1s, 2s, 2p are still Slater orbitals, and we will find there is a problem with the Slater orbital. So eventually what I will do is that for each of them, I will have a predetermined calculation in terms of what will be called Gaussian orbitals. So that is where the name Gaussian will come. So right now there is no Gaussian. I will come to that in tomorrow's class because today it is already 5 past. I'll not bring the concept of Gaussian. But what is important is the number of atomic orbitals. Slater atomic orbital, that number is 9, and that will determine by Hartree form. Many people ask how many orbitals will be generated. That will be totally dependent on this number. And this is called a minimal basis. but the minimal basis is not often good enough. So the same methane, I will try to do a little bit better. So for carbon, instead of using 1s, 2s, and 2p, the chemists realize that whatever chemistry takes place in methane, or whatever chemistry takes place, they're actually in the valence orbitals. I hope all of you appreciate that the valence orbital takes part in chemical bonding. Which are valence orbitals in carbon? 2s and 2p. 1s is core, right? That's core. This is valence. So then the chemists would say that let us do a better job with the valence orbitals. And I will now artificially generate, because it's a basis set, I don't care how I generate mu. I will artificially generate 2 more 2s and 2p orbitals. I will call this 2s prime and 2p prime. How will I generate? Anyway, they will be all generated through Gaussian. I will come to that next class. So my number of carbon orbitals now become 1s, 2s, 2p, 2s prime, 2p prime. This I will leave it as it is. I can also generate 1s prime, but this is not so important. Today, most of the basis set they don't generate this. They just generate core once, but the valence they generate twice. This is the next step. If I do the same thing, then what will happen to the hydrogen? Hydrogen, of course, has no core. It has only valence. Since I have 2 sets of valence, it will become 1s, 1s prime. The other hydrogen will also have 1s, 1s prime. Remember, I'm doing methane. Now calculate the numbers of K. For carbon, you have 1, 2, 3, 6, 9, right? That's 9 instead of 5. We have added 4 functions. 1 sp means 4. 1 plus 3. This is 2, 2, 2, 2. It's very easy. This is just arithmetic. Everybody will be able to understand. Simply calculate the numbers. That is 17. So for the same problem, now K is 17. Number of occupied, n is constant. So number of occupied spin orbital is still same, 5. What has happened? The rest has all gone into unoccupied orbitals, 12. But each of the quality of the orbitals, quality of the binding has increased because I have increased this K. I have told you, more the merrier. This basis set is now no longer minimal basis set. This is the minimal, where at least 1, 2s, 2p, 1s, 1s. This basis set, what do I name? And now there are names. See, basis set I can keep on doing. Why do I give names? Names are only for people to immediately identify, acronyms, right? So I have to give an acronym. The acronym that is usually given is the following, that whenever I'm adding, I'm adding what is called zeta. You know what is zeta? Zeta is an exponent of, oh, sorry, I didn't write this. Yeah, I didn't write this for the hydrogen atom. It was not important, but there is a zeta here. So there is an exponent in each of these, in each of these you can put an exponent. Although for the hydrogen that is 1, so I didn't want to write it. But eventually for all flatter orbital, they will be multiplied by number. Exponent is just a number, very small number. And that's very important. So I should write it from the beginning just so that you don't miss it. Yeah, I'm sorry about that. So there is a zeta that I'm adding. So that is simply called Z. And then how many valence I'm taking? 2 sets. So 2 sets of zeta for valence, either carbon and hydrogen, and this particular basis set will now be called double zeta valence. I hope it is very clear. The name nomenclature is very, very clear. So double zeta valence means only for the valence I'm using double zeta. If olden days people used to double zeta. What does double zeta would mean now? This is okay. For carbon, I'm going to use 1s prime. So this will become 10. It will become 18. Only one more basis. Nothing is going to change. But carbon 1s really doesn't participate in binding. So there is no point using double zeta. You use double zeta valence. So this is gone. Now, quite clearly, I can use triple zeta valence. I hope you have already understood. What am I trying to do? So triple zeta valence is adding another set of S and P. another 4 functions here, one more function here, we got triple zeta, 3. So 4 functions here, 4 functions here, 8, the number will become 25. So if I do the same methane calculation in triple zeta valence, I will have 25 orbitals. Of course, occupied will still remain 5. This is going to become 20. So if you are doing a DFT calculation in a basis, you should be immediately able to check if the calculation is right by counting the number of orbitals. They are printed. All the orbitals are printed, occupied as well as unoccupied orbitals. The number should match with your calculations. In addition to all these, we use what is called the polarization function. So for example, for carbon, I'm going to use a D function. For hydrogen, I'm going to use a P function. They are called polarization. So essentially, it is a function with an angular momentum, which is higher, one higher than the valence. So I hope it's very clear what I'm saying. So the valence angular momentum highest is P. So one higher D, hydrogen was S, one higher P. Now, of course, carbon doesn't have D, hydrogen doesn't have P. Many people get confused. Why am I using? No, it has nothing to do with the valence orbitals. It is something to do with this, the question that Subhajit asked. That is a very relevant question because this has to be as large as possible. It has nothing to do with the atom valence orbitals. This is a mathematics. To make this mathematics as good as possible, I have to use as large a K as possible. More the merrier, larger the better. So I'm going to use a D and a P, nothing wrong. And this will be called polarization function. Usually, I will use only one D function and one P function. Such a basis will be called double. So with combined with double zeta. Let's say combined with double zeta, if you use valence, then it will be called double zeta V valence, DZVP, double zeta valence polarization. If you combine with the triple zeta valence, this will be called TZVP. Again, many of you have seen these basis sets in the literature. Please remember, when I'm going to do the basis set, it's going to continue next class, of course. I can't do all basis sets in the literature. I will just give you an idea what the basis set means. And there is a plethora of basis sets. It's just impossible to do. So, but there are different names of this basis set, double zeta valence polarization, triple zeta valence polarization. When I will bring Gaussian, you will see that the names will also change a little bit, which will reflect the Gaussian as well as this. So the names will be further refined. At this point, I can say double zeta valence polarization, triple zeta valence polarization. In addition, many of these calculations which requires very fine calculations, you require diffuse function. I'm going to come to that in the next class because today it's already late. So I have to get diffuse functions also in addition. So as I said, I'm just increasing the value of K as much as possible, but with an eye. So when I'm going to use diffuse function, you will see that diffuse functions will be used when the long range interactions are very important. So anion, weak interaction, excited states, their diffuse functions will come in, not everywhere. But today, polarization is a must. No calculations can be done without a polarization function. I can tell you, just double zeta valence, triple zeta valence is not acceptable. These will have a different name when I come Gaussian, like 6311G star, etc. I'm going to come to that in next class. Before that, I have to explain why Gaussian, because so far I'm only talking of atomic orbital. There's later. So what is the problem of the atomic orbitals as such? And why do I require a Gaussian orbitals to implement the same basis set? But as you will see, the number will be governed by this later orbital, atomic orbital here. So the numbers are already fixed. The number of molecular orbitals are already fixed to this basis set. So I have today done minimal basis, double zeta valence, as well as double zeta, triple zeta valence, as well as triple zeta. It's very easy. And then various polarization function like triple zeta valence, PP, etc. All in terms of Slater orbitals. I have not brought in the concept of Gaussian functions yet. I'm again repeating, that will come in the next class, and that together will become the modern basis set language. So the language itself will become a little bit more refined as I will bring in the Gaussian. I think with this, I will stop today. I've already started basis function, and I think I've already told you how to do the calculation. That is very, very important. And this is a very easy calculation. People get very confused whenever I ask, how do they calculate number of molecular orbitals? But it is so simple that it is just, you don't need to know any quantum chemistry. Believe me, no quantum chemistry is required, right? It is just counting orbitals and adding. Forget about all the quantum chemistry. So the basis set is a very, very easy thing. All right. I think, is there any question? It's already 8:15. Although I started late, but it's already 8:15. I should stop now. Is there any question? So the basis set will continue tomorrow. And after that, I will go to the functional, exchange and correlation, because I have left that. How do you do exchange and correlation functional? And then some application. So that I will try to end tomorrow, but let us see. Are there any questions? Otherwise, I will stop. Okay.
Yes.
Yeah. So let me stop now. Yeah, and tomorrow also 6:30. So please join in time.
No, I went South Kolkata and I forgot it basically.
No, that's okay. That's okay. No, the key, I don't know. You cannot change it permanently. No, for tomorrow's class.
I have sent you key to you, so now you can.
Okay, fine. No problem. Yeah, thank you. Anyway, you come and join. No problem. But I'm not saying that. So.
Anyway,
so
tomorrow I will be here.
Yeah, if you are there, I'm very happy. So, but without the key, it was difficult, and I think then Suman probably helped us.
Yeah.
So I thank you, Suman, also. All right. So I think Subhajit will close it today. Subhajit.
Yes, sir.
Okay.
Thank you.
Yeah.
Thank you.
Okay.
Yeah.
Thank you very much, and we'll meet tomorrow at 6:30. Okay. Welcome.
Okay. Bye.
Yeah.
I'll end now.
Yeah.